Okay, so going over very briefly the answer key to the homework quiz 4. The PDF of this, a scan of it, will be posted so you can actually compare it. You're not really necessarily using this video, but there are different versions of the quiz questions. So depending upon the numbers you had in yours, you could have had for your lower temperature a range of 3 different temperatures, and for your upper temperature a range of 3 temperatures. First page is the diffusion coefficient calculated for all of those. So if you want to check your diffusion coefficient, find your 2 temperatures, one of these first 3, one of these bottom 3. So check each of your 2. On the next page is just determining what does the RFZ equal. 3 different variations of it based on your surface concentration of carbon. There are 3 different possibilities. The initial carbon and the goal carbon is the same for everyone's, but we get 3 different ERFZs using a series of different temperatures. So based on your ERFZ values, which this doesn't involve temperature yet, we can get 3 different interpolated values of Z. So find the one that applies to you. That's just based on the surface carbon that you have. And then the next pages are broken down by temperature groups. So if your lower temperature was 800 and your upper was 975, what was your surface carbon? 125, 135, or 145? Find the one that applies to you, or the next temperature ranges, or the next temperature ranges. So you've got to find the one that applies to you. Now, one of the things going through here, all of our delta T's in this particular example turned out to be negative. So there's, like, for example, negative 11.8 hours, which actually means this takes longer when we increase the temperature. That was not intended to be a trick question, but I can explain what happened and then explain why it takes longer, because it is counterintuitive. First off, we've got a nice textbook here, and this is a pretty common statement within a manufacturing or a material science textbook. Something to the effect of, let's see, carburizing temperatures may range from 788 Celsius to 1093 Celsius, but usually lie between 899 Celsius and 949 Celsius. Really, those are based on Fahrenheit. That's 1450 Fahrenheit to 2000 Fahrenheit, roughly. So here we go. The higher the temperature, the more rapid the carbon absorption, but also the more furnace deterioration and undesirable grain growth. Okay, that's a pretty typical statement. The higher the temperature, the more rapid the carbon absorption, which means it goes faster. So that's a pretty typical statement. That's what I was always taught. We found a case, obviously, where that is not true. So here's part of my issue with textbooks is these generalized statements. You notice if you've had me for multiple courses, you've probably never been required to buy a textbook. A lot of times this information gets put in here without complete explanations, without the author completely understanding the content sometimes. And frankly, some of it gets plagiarized, which really bothers me. So I often don't have students required to buy into the textbook racket. So hopping off my soapbox, though, that is a pretty typical statement out of a textbook. We have found a case where that's not true, and here's why. So, oh boy, here's our unit cell models. You guys remember what these are? This one's got an atom in the center of the cube body, so it's body-centered cubic. This one has an atom on each face of the cube, so it is face-centered cubic. That looks kind of dark on the screen, but I've got the light on. Let's see. A little better. Okay. So, comparing these two structures, let's say my eraser here is a carbon atom. The interstitial site for face-centered cubic that carbon atom is going to go into is going to be right down here in the middle of the cube. If we look around this, that is an octahedral site, and this is like that carbon atom is in a prison. It is surrounded by bonds between iron atoms. Over here in the body-centered cubic, yes, there is, for instance, a atom hanging out up here that's connected to these corner atoms. But the interstitial, the octahedral site for this is right about here. Okay. And there's a lot more opportunity for this to move side to side. This goes back to the atomic packing factors. Remember, the atomic packing factor for face-centered cubic and hexagonal closed pack were maxed out at 0.74. Body-centered cubic had a lower packing factor. That means that the structure overall is less dense. And that means that because it's less dense, these atoms have more opportunity to move around without bumping into something, which makes diffusion easier. And one person noted this on the quiz they turned in. Oops. When we go to compare, let me center this up. We go to compare carbon cube. Let me just start that sentence over. That is unrecoverable. Carbon moving in body-centered cubic iron. The activation energy is 80,000 kilojoules per mole of carbon. When we're talking about carbon going through face-centered cubic, it's 148,000 kilojoules per mole, which means it takes less energy to get the carbon to move through the body-centered cubic iron than the face-centered cubic iron. So fundamentally, at a equivalent temperature like at 900, we should come over here and we should see that indeed it is a lower diffusion coefficient in face-centered cubic than in body-centered cubic, which means it's harder to move in face-centered cubic. And that's because of the complexity of that structure, and it's packed together so tightly that the carbon atom has a hard time escaping the cube. It can do it, and in fact the interstitial site in here is larger than it is in body-centered cubic. We did that math at the beginning of the semester. But there are more bonds in the way. So that's why that happened. So now the logical question is, why do we ever do this in face-centered cubic? The answer is we need to get to steel metallurgy, which is at the very end of the semester, and we'll fit it in at the last minute. But we need to be in face-centered cubic to quench our steel, to change the microstructure into a unit cell that we have not studied yet. We'll add one more unit cell called body-centered tetragonal, and it will make a microstructure feature in steel called martensite. And that martensite is the starting point for a lot of our hardening processes. We'll do a process called tempering it. Well, it does not form from body-centered cubic. It only forms from face-centered cubic. So if we're going to have to quench or rapidly cool our steel, think about like a blacksmith pulling a sword out of a furnace and sticking it in a barrel of water, something like that. If we're going to do a quenching process like that, where we're rapidly cooling red hot steel, we need our steel to be face-centered cubic, to be red hot, and we need to rapidly cool it. So we're just going to combine the processes typically. We're going to make it red hot, face-centered cubic, because we need it to quench. We might as well absorb the carbon while we're doing that. And overall, it should end up saving us some time rather than heating the steel up in the furnace when it's body-centered cubic just to absorb the carbon and then heating it to quench. We'll just go ahead and go to a much hotter face-centered cubic and deal with our quench. So there's other factors that play into why are we going to do this in face-centered cubic when at a relatively close temperature body-centered cubic is faster to diffuse. Hope that clarifies that. Hopes that makes sense. We'll be moving on from here to different failure methods. So be looking for impact failures, fatigue failures, and creep failures. Thank you.